So today's presentation is about how well integrated and complementary design teams, and specifically well-considered engineering design, solutions and analysis methods can enable and maximise development opportunities in and around complex sites. If you've spent much time in the northeastern corner of Melbourne and enjoy a reasonably priced pot of beer, you should recognise the family hotel in the left-hand bottom corner of this image. This hotel, which is heritage listed, and the remaining buildings around it were the challenges and are the subject of today's presentation. So, what does a pub, a religious mission hall and a brothel have in common? That was the joke I was going to start with, but I'm not going to because I'm an engineer. This is a corner of Melbourne in the 1800s, upon which stood the now heritage listed Elms Family Hotel, which was originally built in the 1850s as the old Governor Burke. Next door is the heritage listed City Mission, originally a dance hall built in 1871, and behind those 17 Castleton Place, a former cottage and most likely brothel that is also heritage listed. They're all located on the corner of Melbourne City Grid, for those that aren't from Melbourne, up on the corner of Spring Street and Little Lonsdale, and those of us from Melbourne affectionately call the area Little Lon. So, it's a part of Melbourne's landscape that really is rich with history and tells a story of Melbourne through the last century. The subject buildings and laneways are considered the largest intact portion of Melbourne's notorious 19th century red light district, and we're in an area of substandard housing, poverty, brothels, hotels and workshops. Fast forward to our recent excavations, and thanks to engaged archaeological consultant GML Heritage, who carefully excavated the top metre of site, a lot of interesting things were found. Very old and once expensive champagne and wine bottles, coins, some Aboriginal artefacts, as well as all sorts of other interesting paraphernalia. I don't expect you can read this article, but if you can, it's a letter from a gentleman who had an altercation outside the now Mission Hall, trying to express concern for the welfare of the women inside and the daughter of a woman who was on the street trying to get her out. So, anyway, back to the Elms Family Hotel, and this is what you would have seen if you'd visited the corner of the site over the last 20 years. It's a prime piece of real estate in Melbourne and a site that hadn't been developed for the reasons I'll be going through in this presentation. So in plan view, this is an image that John Wardle Architects produced of the precinct. The bottom right-hand corner is the octagonal Castleton Place building, which is a prominent building in Melbourne skyline. The top right-hand corner is our subject site. The rest of the site had been fully built out. This here is a sneak peek of where my presentation is headed. It's a render of the Spring Street elevation of the John Wardle and Arup collaboration, alongside heritage architects Bruce Trethowan, and encircled by the buildings that I've been discussing at the lower level. So, I've touched on the history and above ground built conditions, but with all the character above ground, why are you listening to a structural engineer? The answer is that there was a lot going on at ground level and below ground as well. So, Melbourne's two alignments of double-stacked city loop underground rail tunnels, as you would have seen in the previous image, and I'll show you in plan, ran directly beneath the site. To top of tunnel, they're about 17 metres below natural grade. To top of the easement, about 10 metres, and when you go down into our basement, the easements are only 6 metres below us. There are 3 electrical easements, or 6 if you include the accesses over. There's a substation serving the precinct, 2 major conduit runs and the access is over, and there are 2 rights of way as well. Alongside those, there are the existing heritage buildings that I've discussed. So, it was in 2012 when Arup and ISPT first came together to discuss this development. ISPT had been working on the site for a number of years looking at various options, which for all sorts of reasons they hadn't been able to realise. It was at this point that we were fortunate enough to be given the opportunity by ISPT to look at, and John Wardle Architects, to look at what an engineering-led solution might look like. So the question is, what did we actually do? So collaborating with our architectural friends, our aspiration was really simple on behalf of ISPT. It was to bring an approach to the project that would enable a development that was commercially viable, that could be built such that rents could be reasonable and they could find a tenant for a significant building on the site. Arup provided all engineering services: structural, civil, geotechnical, building services, facade, fire, ESD, acoustics, traffic and vertical transportation. So full suite of engineering services. Our intent from the outset was to approach the consideration of structural and foundation solutions that would respond directly to the site's constraints and then inform the design. This is somewhat in contrast to perhaps a traditional approach in which a design solution is based on NLA, fit-out requirements or aesthetics and placed onto a site, let's say. So what were our challenges in structural and geotechnical terms? Where can primary structures touch the ground? How do ground plane loadings impact the tunnels in particular? And what were the settlement implications of the foundations we were putting down onto the ground, and what did that mean for the various heritage and brittle brickwork structures around us? To use a mathematical term, our approach was driven by these boundary conditions. Tunnels are tubular concrete structures. They like compression, they don't like decompression, and they don't like localised loads. Easements, as we know, are no-go zones, and existing structures, as I said, were the brittle brickwork on very old bluestone foundations, and they certainly don't like moving around. We assessed the maximum and minimum stress that could be placed on the underground city loop tunnels. We identified and challenged the areas of the ground that we could and couldn't touch based on these easements, and we assessed and identified areas of ground and the site that we could and couldn't touch on the basis of heritage buildings, facades and archaeology. This sketch looks pretty rudimentary, but I'm particularly proud of it because it was produced by me only a few days after we first opened discussions with ISPT, and it gives you a good indication of the constraints to the site. The site's bounded by the blue line on the left and the brown lines on the right. The city mission is in the bottom right-hand corner, substation bottom left, easements running up the page in blue, heritage facades wrapping around, and the two city loop alignments diagonally running across the page. So that was our site, and you could see to some extent why it hadn't been developed previously. So the process was to be one of iterative optioneering of structural framing and foundation concepts that responded to these boundary conditions and constraints. An obvious consideration, but one that is sometimes overlooked in ensuring superstructure construction and norms are adhered to, is the self-weight of various construction types. The benefits obviously lie in reduced foundations, extents, but are emphasised when it is imperative that ground pressures are minimised and limited founding locations are available. This study led us to consider numerous options for the building's structural materiality. Traditional reinforced concrete at the heaviest end of the spectrum, lightweight concrete products, steel and timber at the other end. The impacts on various superstructure elements also needed to be carefully considered due to the requirement for raking structures and their associated kicking forces, as well as the need for transfers and open spaces, obviously at the lower levels. We converged on a composite steel and concrete solution, combining relatively lightweight construction with buildable geometric flexibility and an ability to easily integrate bracing. If not considered carefully, the drawback of lighter weight construction, as the structural engineers in the room will know, can be acoustic and unwanted dynamic responses. This slide shows a dramatically factored image of a critical vibrational mode, and it's relevant to this building as it drove a lot of the steel sizes up the building as we tried to maintain the lightest weight structure possible. In simple terms, we assess, in doing a vibration assessment like this, we assess floor plates' response to people moving at various speeds, perceptibility of the cause vibrations, and then we benchmark those against commonly accepted global guidance. Another part of this key decision on building construction type, materiality and form was the building's lateral stability and movement behaviours. At a high level, building importance level to the NCC is the governing factor in determining the natural wind and earthquake events that a building is to be designed for. This determination relates primarily to a building's use and population. For our building and its integration with heritage structures at low level, this needed some focus and agreement to ensure appropriate outcomes and enable optimisation. To upgrade heritage buildings for current earthquake loadings is often impractical or can result in very poor architectural outcomes. For our heritage buildings, we proposed and ultimately agreed a lower level of importance and a further reduction to 67% of the applicable new equivalent building loads, earthquake loads. This is considered in accordance with code guidance to protect life safety whilst enabling appropriate heritage outcomes post-strengthening. It does, however, mean the heritage components must be isolated from the new building extent in a structural sense. The new building could then be considered in isolation as an importance level 3 building in common with the majority of large-scale buildings in our CBD. So by this point, we were armed with the ability to establish the loads imparted by the building superstructure on the ground for any given geometry. This is hopefully where it gets a little bit more interesting for the structural engineers in the room. From here, we established techniques to assess and control the pressures exerted on ground zones by various superstructure options. We did this by using springs to control the maximum and minimum stresses, as well as types of stress and loading that could be exerted on areas of the ground. And therefore, we're able to control the pressures on the tunnels below, adjacent below-ground substation, heritage foundations and easements. This required careful iteration of superstructure, substructure and ground models and provided interesting results in relation to superstructure's performance and load paths generated. Critically, it enabled us to understand where and which potential stability elements were going to be most effective and could be implemented within our constraints. The images on the screen are pretty straightforward, but the most interesting process we went through was this ground stiffness exercise. And what we did, those springs, squiggly lines on the bottom of the right-hand image, we built exoskeleton models and all sorts of models of different bracing systems, and we tuned those springs such that in any given model, the appropriate stresses on the tunnels weren't being exceeded. What that did was reverse engineer up the tower various stability options of where the load wanted to go. So we used meshes to establish where loads wanted to go in the superstructure. We could then assess where we should be putting walls and bracing, and we could propose that and work with our architectural friends to implement those. This is a ground stress section, obviously. Complementing this superstructure iteration were our methods of ground stress assessment. This is an output from a ground stress analysis showing the core raft stresses dissipating into the ground below. We were able to combine these models with our superstructure models to create an analysis workflow that would ultimately converge on an acceptable superstructure and founding solution. And that was probably the differentiator and key to our success. So what about architecture? This whole process was a close collaboration with John Wardle Architects. Amongst many, there were two clear architectural and heritage geometric constraints that we needed to address. Both required substantial rakes or cantilevers within the building's facade and thus vertical elements, and came as a result of heritage sensitivities over the Elms Hotel and a need to achieve a practical floor plate above the constrained ground plane and buildings. Critically, these prohibited the ability to establish a primary stability structure on the eastern facade and meant that the already spatially constrained side core could not all be taken to ground. So for the non-structural engineers in the room, in simple terms, a rectilinear building like this can be stabilised by a torsionally stiff core or a bracing system on best part of three sides. The images on the screen are three of over 50 models that we ran through the process that I described briefly earlier. The right-hand image is where the building has landed and is being constructed at the moment on site. Looks a little bit clunky when you don't put the architecture around it, but the trusses are either embedded in the facades or embedded in the side of fire or intertenancy stairs, and the lateral trusses are also well hidden within the architecture. So in terms of getting approvals, a critical part of these developments over City Loop rail tunnels is authorities. As Arup closed in on the final solution, we continued to carry out more and more detailed assessments of the final loads that were going to be going down through our foundations and onto the tunnels. This is just a nice plan view image of ground pressures under our side core foundation for one of the many load cases that we assessed. And this image shows a cross-section of the entire site under a similar load case. It was these models that enabled our accurate assessment of the real loads on the tunnels and helped us maximise the development opportunities for the client. For the engineers in the room, geotechnical conditions, as they can be in Melbourne, up the top with silty clays over Melbourne formation siltstone, only about 4 metres down. This was very helpful to us really, and importantly facilitated the shallow foundations, good spread of building loads that eventually found their way down to the tunnels. Final technical consideration was the basement excavation, which proved to be one of the most critical tunnel stress considerations. The unloading of circular tunnel structures like this can result in elongation vertically, which results in tensile forces in the circular structures. So ultimately it was the combination and the use of 3D building models integrated into superstructure and substructure analysis models that enabled sufficient well-considered options to be assessed and led to a convergence on a solution that would ultimately be built. This, in combination with the integration of structural and geotechnical analysis, as is possible when the two disciplines are able to collaborate in real time, was the enabler and differentiator for this project. Through our innovative analysis, an intelligent, coordinated, readily constructible solution was achieved. We managed to design a building that was of a sufficient scale to yield a level of rent that would ultimately enable the building to stack up commercially. 15,000 square metres of NLA in a side-core 16-level office building that is now fully let. All of this was a close collaboration with ISPT, John Wardle Architects, Bruce Trethowan, Heritage Architects, RCP project managers, Ryder Levitt Bucknell, Urbis, and now ProBuild Constructions. The scheme combines integrated facade, rooftop and superstructure bracing elements to side core and shallow foundations to successfully facilitate an architecturally stunning building with a multi-purpose floor plate in a sensitive urban environment. The design maximises floor plates and creates opportunities for new contemporary workplaces. It integrates the lower floors with the heritage buildings and includes an outdoor garden mezzanine to assist with the break between the superstructure and the heritage. It facilitates horizontal and vertical connectivity for improved team-based collaboration and performance. On a site that had lain undeveloped for many years, Arup and our collaborators have successfully realised this fantastic development through well-considered and intelligent site-specific engineering and architecture.